Earlier in this unit, we've seen gravitational potential energy written and described in the following way. Potential energy U is equal to mgh. Now this is of course assuming that the force of gravity near the surface of the Earth is a constant, that is mg. Recall of course from Newtonian gravitation that this is not the case. The force of gravity, according to Isaac Newton, is the following expression. Capital G, the universal gravitational constant, multiplied by the product of the masses, divided by the distance squared. Remember that near the surface of the Earth, the force of gravity treated as a constant is only an approximation of what we see here. Therefore, what we have to answer is the following. Is the force of gravity in its Newtonian form here a conservative force? And if so, what is the potential energy associated with it? So to answer those questions, what we have to do is we have to calculate the work done by gravity in this form over a closed path. Let's go about doing that calculation now. Okay, so let me go ahead and do some erasing. And now we're going to do the following. Calculate the work done by gravity over a closed path. Okay, there's a specific way to set up this calculation, and it's most easily conceptualized in the following manner. Okay, let's say right here is the Earth, like so. And then here's the center of the Earth, and remember that mathematically we treat the entire mass of the Earth as a point at its geometric center. By definition, we define the center of the Earth as the origin. Okay, and then we have an object here of mass m that's initially at position A. It then moves from position A to position B, uphill, if you will, and then it goes back downhill from position B to position A once again, thereby completing a closed path. So we're going to calculate the work done by gravity over that closed path. Immediately, there are some complications. The first, of course, is that gravity is not a constant. It varies with distance from the center of the Earth. So then, therefore, we're eventually going to have to set up the following integral. Recall that this line integral right here is the true definition of work. It takes into account a curved path of some sort, and in this case, the varying force of gravity. And then we get to the complications of the path itself. What we're going to do is take the path, say from A to B, and break it up into a series of small steps. There is a precise mathematical way of describing what I'm about to show you, but we'll go through that description qualitatively. Here's how we'll begin to picture this. Okay, so let's break up the path from A to B into a series of small steps. Okay, using unit vectors in polar form, there's a specific way of describing this, but here's how we'll just qualitatively describe it. Okay, so right here's the Earth once again. Right here's my origin. Right here's the mass of the Earth. Right here's our mass m at position A. And then what we're going to do is move from position A to position B, but in a series of small steps. The steps are basically done in two ways. The first step that we'll do is radially outwards from the center of the Earth, like so. And then we'll take a second step, and this second step is going to be along a circular arc, where the center of that circle is the center of the Earth, like so. And then we'll step again. In this case, we'll once again step radially outwards from the center of the Earth, like so. And then we'll take a step along a circular arc. Once again, the center of this circle is the center of the Earth, the origin, like so. And so on and so on and so on as we go from point A to point B on the diagram. Okay, now right here is once again a step in the radial direction. Think of this as being analogous to the vertical direction near the surface of the Earth. Okay, and then right here is a step along a circular arc where the center of that circle is the center Earth. Once again, there's a precise way of describing all of this mathematically with specific types of unit vectors, not necessary for our purposes here. Think of these steps along the circular arcs as analogous to taking a step horizontally near the surface of the Earth. Now, when you take a step horizontally near the surface of the Earth, your displacement vector is perpendicular to the force of gravity straight downwards. So then therefore no work is done by gravity when you take a step horizontally. Same thing here. The force of gravity, remember, is radially inwards towards the center of the Earth. So then therefore every time that we take a step horizontally, that is along a circular arc, no work is done by gravity. Therefore, the only steps that we have to worry about are the steps in the radial direction, the vertical direction, if you will. This then allows us to greatly simplify the diagram on the top board and simplify the calculation. So let me just go ahead and write that here briefly. Okay, along these horizontal steps, if you will, along these steps, no work is done by gravity. The reason for that is because the gravitational force vector, which is inwards towards the center of the Earth, is perpendicular to this displacement vector when we step along this direction, along this circular arc. So then therefore, the only steps, if you will, that we have to worry about are the steps in the radial direction. That allows us to simplify the diagram on the top board in the following way. Okay, so let me do some erasing here. Like so. Okay, and now let's change the starting diagram in the following way. Okay, now we'll say that our point A is right here. Here's mass M, and our distance away from the center of the Earth, this radial description here, we're going to refer to as r sub A. And then once again, the only thing that matters is taking a step in the radial direction, that is the vertical direction. So now let's just say that right here is position B, and then with respect to the origin, the distance that we are from, at position B rather, is r sub B. And now we have to calculate the work done by gravity as we go from A to B, and then backwards from B to A. Here's now how we set up the integral. The work done by gravity is always going to be the following calculation. It's analogous to the work done by the spring force. Recall how we calculated the work done by the spring force. Let me jump to the lower board here to once again refresh your memories. So this is analogous to calculating the work done by the spring force. So recall how we defined things. Let's say that here is a mass attached to a horizontal spring. Right here is the equilibrium position. And then by definition, we defined the infinitesimally small displacement dx from equilibrium as a positive number. And then the spring force was back in the opposite direction, back towards the equilibrium position, and the spring force then therefore was thought of as a negative number. So when we calculated the work done by the spring force, we always had the following integral. Integral of minus kx dx. And then the only thing that changed from situation to situation are the limits of integration. Same idea here, now we're talking about the force of gravity. So going back up to the top board. Okay, by definition, we step outwards from the origin like so along a displacement dr. We think of that displacement as positive by definition. However, the force of gravity acts back in the opposite direction, inwards towards the center of the Earth. So then therefore, by definition, we think of the force of gravity as negative. This then means that we write the integral itself to calculate the work done by gravity in the following way. Negative g mm over r squared dr. And then the only thing that changes are the limits of integration from situation to situation. So now let's see what happens as we go from A to B and then backwards from B to A. Okay, let me go ahead and erase here. Okay, and now let's set the calculation as we go from A to B. So the work done by gravity is going to be the following integral. Negative g m m over r squared dr. But now we go from r sub a to r sub b. Let's go ahead and find the antiderivative here of this integral. Now to do so, I'm going to take out the constants, the negative g m m out in front like so. And just so we could use the rules for integrating polynomials, let me write the 1 over r squared as r to the minus 2, like so. And now recall the rule for integrating polynomials. You take the value of the exponent and you increase it by 1. When you increase negative 2 by 1, you get negative 1. And then you divide by that new exponent. So that then gives us this. Like so. And then we evaluate this from r sub a to r sub b. Now before I plug in the limits of integration, let me just go ahead and clean this up a little bit. This negative sign cancels out with this negative sign here, and let's just write this guy here in the denominator in the following way. Like so, as we go from r sub a to r sub b. So you plug in the upper limit of integration first, r sub b, plug in the lower limit of integration second, r sub a, and you subtract it as you do. Therefore, you end up with the following. We end up with g m m over r sub b minus g m m over r sub a. And then we go backwards. When we go backwards, all that we do is we switch the limits of integration. Now we go from b to a. Okay, so now from b to a, the work done by gravity is once again the exact same integral as before. Integral of negative g m m over r squared dr. But now we go from b to a. So from r sub b to r sub a. When you switch the limits of integration, ultimately the only thing that happens when you get to the end of the process is that these two terms reverse. You just end up with this. Like so. So we end up with these rather complicated functions here as a result of the integration, but now add the two terms together. That is the work done as we go from a to b, these guys here, plus then what happens when we go back from b to a, these guys here. If you add everything together, notice that everything cancels out, and so then therefore the work done over the closed path is 0. Therefore the force of gravity in its Newtonian form is conservative. No surprise. Okay, so note the work done by gravity over the closed path is 0. Therefore, no surprise, gravity in its Newtonian form is a conservative force. So think of it this way, on the diagram above, imagine that an object is thrown from A to B. It's basically thrown upwards. So then therefore its kinetic energy decreases as it does, and then therefore its potential energy increases as it does. In other words, the kinetic energy is being transformed into potential energy as the object rises upwards. And then if it, say, falls from B back to A, then that potential energy is transformed into kinetic energy as it falls. No surprise, gravity in its Newtonian form is also a conservative force. Okay, then the next step is to quantify potential energy itself in its Newtonian form. I'll do that in the next lecture.